All right, so here's one more example of how you might do an angular momentum problem, okay? This is a real common problem to have something like this. Flywheel rotates without friction at an angular velocity of 600 revolutions per minute. Oh, well, that's great. Thanks a lot for that. On a frictionless vertical shaft of negligible rotational inertia. The second flywheel at rest has a moment of inertia 3 times that of the rotating flywheel and is dropped onto it. Because friction exists between the surfaces, the flywheels very quickly reach the same rotational velocity after which they spin together, okay? So this is like an inelastic collision, right? So this would just be like 2 cars coming at each other and then sticking together after the collision, okay? Use conservation of angular momentum to determine the angular velocity of the combination, okay? And then something about the energy, okay? Right, so again, this would be just like car 1 comes in to car 2, right? Maybe like this car is initially at rest, this guy comes in, and then they stick together afterwards. Okay, so like here you'd have mv plus mv would be their combined mass and velocity. Okay, so this is exactly the same thing except for that it is angular. Okay, so initial angular momentum equals final. Okay, so I'm just going to have I1 omega 1 initial plus I2 omega 2 initial equals I1 plus I2 omega final, right? Because it's inelastic, okay? All right, let's see. The second flywheel at rest is dropped onto it, has 3 times the moment of inertia. Okay, so, oh, it's at rest anyway, so who cares? Okay, so that's at rest. Are they both at rest? No, flywheel rotates. Okay, so the bottom one is rotating. Okay, so I1 omega 1 equals I1 plus 3I1 omega f, right? Because it said that one was 3 times as much. Okay, so I1 omega 1 equals 4I1 omega final. All right, so just get rid of those. And so then omega final is going to be omega 1 initial over 4. Okay, because now it's 4 times as massive, which makes sense. Okay, so then if I do 600 revolutions per minute divided by 4, okay, so 150 rev per minute. Okay, and I can put that in radians per second if I want to. I don't really feel like it right now, honestly, but I can put it in. It doesn't really ask, does it? No, that's fine. Okay, revolutions per minute is fine then. Okay, all right. What fraction of the initial kinetic energy lost in the coupling of the flywheels? Okay, so now we are going to have to convert those, I think, right? Because you're going to have to use I would convert them. Okay, all right, so here, I'm kind of running out of space. Okay, so the initial would be, I might have to erase something, 600 revolution per minute. Okay, 1 minute, 60 seconds. 1 rev is 2 pi radians. Okay, so 600. Okay, so 10 times 2 times pi, might as well just get a number, 62.8 radians per second was the initial. Okay, and then the final would be 150 divided by 60 times 2 times pi, 15.7. Okay, or a quarter of that, right? Radians per second. Okay, all right, so initially, right, if I do the K rotational initial, 1/2 I omega squared, okay? The initial I, does it give us the I? Because it just says fraction, right? Okay, so let's just leave it as I. Well, I wonder if I even want to do this at all with numbers. You know what, it's probably easier if we just don't even put numbers in this. Let's just leave it in variables. Omega naught squared, okay, that was the initial. Okay, and the final was 4I, but it was also 1/4 squared, okay, of the initial, right? Because the velocity was 1/4. Okay, so if I want the initial is I omega squared, and the final will be 2. Oh no, let's just leave it as 1/2 actually. Okay, so that would be 4 over 16. So that would be I omega squared, right, divided by 4. Okay, right? Because it's 4 times the speed, but, or 1/4 the speed, but that's squared, but it's also 4 times the rotational inertia, okay? Right, so afterwards, you only have 1/4 of the kinetic energy that you had before, okay? So that would be, I guess, what, a 75% loss, right? Or only 25% remains after.